Good evening to all of you. Today we are going to have lecture on thermal remote sensing. Uh, Thermal infrared energy is emitted from all objects that have a temperature greater than absolute zero. So if you will see in the nature, all the objects which are existing, they all are having the temperature, particularly on the earth surface, they are having the temperature greater than the absolute zero. Therefore, all the features we encounter in landscape on a typical day, sun, vegetation, soil, rocks, water, and even people, emit thermal infrared electromagnetic radiation. Humans sense thermal energy primarily through the sense of touch. Our eyes cannot detect differences in the thermal infrared energy because they are primarily sensitive to short wavelength visible light from 0.4 micrometer to 0.7 micrometer. Our eyes are not sensitive to the reflective infrared that is ranging from 0.7 micrometer to 3 micrometer, or thermal infrared that is covered under 3 micrometer to 14 micrometer range of the electromagnetic spectrum. Fortunately, engineers have developed detectors that are sensitive to thermal infrared radiation. These thermal infrared sensors allow humans to sense a previously invisible world of information as they monitor the thermal characteristics of the landscape. Here, this slide shows the importance of the thermal data set. Here, if you'll see the right hand side image is the image of the multispectral data set of Aston, and the left hand side image is the Aston nighttime thermal image. And from this structure, after seeing this structure, we can easily say that this is the image of the volcanic structure. So now from the optical multispectral data set, since the volcano is not currently this is not erupting, so if it is not erupting, so from the optical multispectral data set, it is not possible to say that this is an active volcano or dead volcano, because if it will erupt the lava, or if you will able to see the lava flow from the optical multispectral data set, then only we can say that this is active volcano. But we cannot say that this is dead volcano. For that, if we will see the nighttime imagery, which is shown in the left side of the slide. So if you will see the left slide image, so that is the Astra thermal data set. So thermal data sets, thermal sensors, basically they are going to sense the thermal infrared energy emitted from the earth surface. So here if you will see that for the volcanic structure, like here the energy emitted by the rocks, and other portion of the volcano, that is very low, very low emission is there, so that we are not getting any kind of high heat information for this location. But if you will see the center of the volcano, that is basically the crater, center of the volcanic crater, if you will see this area, so this is showing very high temperature, because very high energy is sensed by the thermal sensor. So very high energy is emitted for this from this particular location, so that energy is sensed by the sensor, and finally we can say that this is appearing as a very bright pixel. So very bright pixel in thermal data set shows that very high energy is detected. Now from this one can say that this volcano is not dead, because the center is having very high heat. It means that magma is still there inside the crater. Now there are several other advantages of thermal remote sensing. In this image, this is the like aerial data set, optical multispectral data set. The left side is the two color composite image of the Baton city, and the right side image is the thermal data set for the same area. So the yellow and the red areas are hot in the thermal imagery and generally correspond with roads and buildings. Blue and green areas are cool and indicate water and vegetation. If you will see that blue and green area, these are basically water and vegetation. The bright red areas in this image, we are talking about this thermal imagery. This is having temperature about 65 degrees centigrade, that is approximately 149 degree Fahrenheit. Dark green and blue areas are having temperature around 25 degrees centigrade, like the water body and vegetation, and that is approximately 77 degree Fahrenheit. The solid blue swatch of color flowing down the left side is the Mississippi River. So here we can see that this is the Mississippi River, and this is showing very less temperature, approximately of the 25 degrees centigrade in the thermal imagery when we are comparing it with the urban structures like buildings and roads. Now this is another image, optical multispectral two color composite image. Left side and right side is a thermal image. So in this image what we are going to see, the white area, mostly rooftops, the white areas which are there in the optical multispectral imagery, these are basically the rooftops, and they are showing approximately 60 degree centigrade temperature, that is approximately 140 degree Fahrenheit, and the dark areas are approximately like water body, which is shown here in the green color, as well as water body that is shown in the blue color, as well as the green color area. They are having the temperature approximately of 29 to 36 degrees centigrade, that is having 85 to 96 degree Fahrenheit. The hottest spots are buildings, seen as the white rectangles of the various sizes, and the rail yard in the orange color is also shown here. So this is also showing very high temperature. Now when we are talking about the thermal infrared spectrum, first of all we should know that like infrared is used in optical multispectral remote sensing also. That is the reflected infrared, reflected portion of the infrared, that is having the wavelength range from 0.7 micrometer to 3 micrometer, and that is subdivided in the near infrared and mid infrared. So near infrared having range of 0.7 micrometer to 1.3 micrometer, and mid infrared having range of 1.3 micrometer to 3 micrometer. Now 3 micrometer to 14 micrometer is the thermal infrared range which is used in the remote sensing imaging. Now when we are talking about thermal infrared range, so sometimes like theoretical range is going from 3 micrometer to 100 micrometer. In some books you are also going to see the range from 3 micrometer to 20 micrometer. But most remote sensing applications make use of 3 to 5 and 8 to 14 micrometer range, because 5 to 8 micrometer is the absorption band, like all the information which will be radiated by the surface in 5 micrometer to 8 micrometer will be absorbed by the atmospheric water vapor. So that particular range could not be used for the imaging purpose. Now we have talked about the thermal infrared as well as the reflected infrared. So the main difference between the thermal infrared and near infrared is that the thermal infrared is emitted energy, whereas the near infrared is the reflected energy, similar to the visual light. So that the reflected infrared or near infrared is also used in the optical multispectral remote sensing. Now these are some important terms, terminology which we are frequently using in thermal remote sensing, and those are kinetic heat, temperature, radiant energy, and the radiant flux. The energy of particles of matter in random motion is called the kinetic heat, also referred to as internal, real, or the true heat. All objects having a temperature above absolute zero, or you can say that 0 degree Kelvin, or minus 273.16 degrees centigrade, or this is also referred as minus 459.69 degree Fahrenheit. So the absolute all the objects above absolute zero exhibit the random motion. When these particles collide, they change their energy state and emit electromagnetic radiation. So like here these are going to emit, because we have already talked previously, like all the objects above absolute zero, they are going to emit the thermal radiation. Now the amount of heat can be measured in calories. Calorie is defined as the amount of heat required to raise the temperature of 1 gram of water 1 degree centigrade. We can measure the true kinetic temperature or concentration of this heat using thermometer. We perform this in situ temperature measurement when we are ill, because we all have used the thermometers to measure the body temperature. So when the body temperature is high, then we are declaring that okay, the person is having fever. So but at that time we are directly touching the object or touching the body with the help of the thermometers, so that the temperature could be recorded. We can also measure the true kinetic internal temperature of soil or water by physically touching them with a thermometer. Now the word kinetic heat, this is basically referring the true heat or the original temperature or the internal heat of the object. Fortunately for us, an object's internal kinetic heat is also converted to the radiant energy. Radiant energy is the energy which will be sensed by the radiometer, and this is often called the external or the apparent energy. The electromagnetic radiation exiting an object is called radiant flux and is measured in watts. The concentration of the amount of radiant flux exiting an object is its radiant temperature. So when we will have the information of the kinetic temperature, then we can find out the information of the radiant temperature. They are related to each other, or they are correlated to each other, but we will see what is the relation between, in the next slides we are going to see what is the relation between kinetic temperature and radiant temperature, because generally what we are expecting, like when the internal temperature or the true temperature or the kinetic temperature of the object is high, so it is expected that the radiant temperature will also be high. Or we can say that when the kinetic heat is very high, then the radiant heat will also very high. But this is not true. We will see in the next upcoming slides. There is usually a high positive correlation between the true kinetic temperature of an object and the amount of radiant flux radiated from the object. Therefore, we can utilize radiometer placed some distance from the object to measure the radiant temperature, which hopefully correlates well with the object's true kinetic temperature. This is the basis of thermal infrared remote sensing. Now, unfortunately, the relationship between the kinetic temperature and the radiant temperature is not perfect, with the remote sensing measurements of the radiant temperature always being slightly less than the true kinetic temperature of the object. This is due to the thermal property. That property is also known as emissivity. Here we are going to see the atmospheric windows in the electromagnetic spectrum. So here particularly when we are talking about the visible lens, so here you can see that in the visible lens from 0.4 micrometer to 0.7 micrometer there is spectral atmospheric window, and when we are talking about the reflected infrared, so 0.7 to 3 micrometer there is atmospheric windows. Now when we are coming to the thermal infrared, so in thermal infrared the atmospheric window is there from 3 to 5 and 8 to 14, and here you can see that all the information between 5 to 8 is absorbed by the atmospheric water vapor, so that this 5 to 8 micrometer range of the electromagnetic spectrum is not used for the remote sensing or particularly for the imaging purpose, but there are also other usage of this band. Now we are going to discuss few laws. So here this is the Planck radiation law, that is also known as the black body law of the Planck. So Planck's black body radiation law describes the electromagnetic radiation emitted from a black body at a certain wavelength as a function of its absolute temperature. So here a spectral radiant exitance that is represented by m lambda will be equals to 2 pi hc square divided by lambda to the power 5, and it will multiplied by e to the power hc divided by lambda kt minus 1, where lambda is the wavelength, m lambda is the spectral radiant exitance, h is the Planck's constant, c is the velocity of the electromagnetic wave or speed of light, k is Boltzmann constant, and lambda is wavelength, and T is absolute temperature in degree Kelvin. Now when we are going to see the black body curve based on the Planck's law of black body radiation, so the total energy a black body radiates and the wavelength of the maximum emittance depend on the temperature of the black body and can be described by the Stephen Boltzmann law and the Wiens displacement law. Basically the Stephen Boltzmann law and Wiens displacement law, these laws are basically derived from the Planck's law of the black body radiation. Now black body radiation curves at different selected temperatures. The law of Planck Stephen Boltzmann, that is the marked area under the 300 degree Kelvin, and the Wien that is represented in the green dotted line are depicted in the figure. The blue bar indicates the visible region of the electromagnetic spectrum, that is your 0.4 micrometer to 0.7 micrometer. when we are coming to the winds displacement law, so this law tells the relationship between the true temperature and the dominant wavelength. So when the dominant wavelength or the temperature is known, so one can measure the other information. Suppose here the according to formulas, the dominant wavelength will be equals to K divided by T, where K is constant, that is 2898 micrometer degree Kelvin, and T is the temperature of the body at in the particular wavelength. So when the temperature will be known, so with the help of that temperature, what is the dominant wavelength, that could be measured. So in the next slide we are going to see the example. So here example is given for the earth surface. The average temperature of the earth is approximately 300 degree Kelvin. So when this 300 degree Kelvin, so when we will compute the dominant wavelength of the earth surface, so this will be coming approximately around 9.67 micrometer, because 2898 divided by 300 is going to give the value 9.67 micrometer. So generally for the earth observation, because here we can see that the dominant temperature is 9.67 micrometer, so generally for the earth observation purpose, all the thermal sensors, they are designed between 8 micrometer to 8 micrometer to 12 micrometer, because dominant wavelength is near to 10 micrometer. So that most of the earth observation sensors, they are designed in this range, 8 to 12 micrometer. And we can also find the, like suppose one wants to do the drone based survey to find the temperature information. So we can also find out the most suitable wavelength range which could be used in the thermal remote sensing for with the help of drone based survey or the airborne earth observation. So the dominant wavelength provides a valuable information about which part of the thermal spectrum we might want to sense in. For example, if we are looking for 800 degree Kelvin forest fire that have dominant wavelength of approximately, you will divide it 2898 divided by 800, so this will be coming approximately 3.62 micrometer. Then the most appropriate remote sensing in this to do the to find the useful information of the forest fire in between 800 for the average temperature of 8 degree Kelvin will be 3 to 5 micrometer. So 3 to 5 micrometer thermal infrared detectors, they are going to provide the most valuable information for the forest fire, which will be having the average temperature range of 800 degree Kelvin. If we are interested in soil, water, rock with ambient temperature on the earth's surface of 300 degree Kelvin, so we have already seen the dominant wavelength range is 9.66 micrometer. So at that time, the thermal infrared detector should be able to capture the data set in between 8 to 12 or 8 to 14 micrometer. Now we are going to see the Stephen Boltzmann law. So this law tells about the relation between the energy and the temperature. The Stephen Boltzmann law is derived by integrating the Planck's function with respect to the wavelength. So if you will see here, the total energy will be function of the force power of the temperature. So the total energy or the radiant flux will be proportional to the force power of the maximum temperature or the temperature. So if you remove the proportionality constant, if you remove the proportional and so that there will be proportionality constant. So sigma is the proportionality constant, that is known as the Stephen Boltzmann constant. And here this will be a fixed value, so energy will be equals to sigma multiplied by T to the power 4. So when you will have the information of the dominant wavelength, you will be able to when you will have able to dominant wavelength, then you can calculate the dominant temperature. When you will have the information of dominant temperature, you can find out the total energy also in the particular wavelength range. Now when we are talking about thermal radiation, so thermal radiation when we are talking, so generally two temperatures we are going to talk. That one is kinetic temperature, that is the internal temperature of an object, and that is determined by the random molecular motion, so that the energy will be emitted. Energy will be emitted by the object or surface. Another is the radiant temperature. Radiant temperature is the temperature which will be sensed by the radiometer or the thermometer. So thermal scanning detects the energy, which is a function of the temperature. Radiant flux emitted by a body at a given temperature. That is the radiant temperature. Now here we are going to see the relationship between the radiant temperature and kinetic temperature. So generally, in the normal situation, we can expect that okay, radiant temperature may be equal to the kinetic temperature, but that is an ideal condition. This is true only for the black body. So the kinetic temperature will be like for all the gray body or the objects appearing on the Earth surface, they will have higher kinetic temperature and the lesser radiant temperature. Radiant temperature could not be greater than the kinetic temperature. It will be either equal to or less than. Equal to also it is difficult, because equal to get the equal amount of radiant and the kinetic temperature, the emissivity that is represented here by E, emissivity should be equal to 1. And here one emissivity we are going to get only for the black body. So here all the objects appearing on the Earth surface, they will have the emissivity greater than 0 but less than 1. So for all the objects, the kinetic temperature will be higher than the radiant temperature, or we can say the radiant temperature will always be less than the kinetic temperature. Here this is an example in which it has been shown that there is one aluminum block. Half of the portion of the aluminum block is polished by metallic paint, shiny surface, and half of the portion is painted by the black carbon particle. Now you can see that for the aluminum block, kinetic temperature is approximately 288 degree Kelvin. That is approximately 15 degrees centigrade. That is the kinetic temperature. Now here you can see that for the metallic surface, shiny surface, the emissivity is approximately 0.05. And but for the surface which is painted by the black carbon particle, this is having emissivity approximately of 0.98. Now if you put in the formula to calculate the radiant temperature, so as we are knowing that radiant temperature will be 1 by 4th power of the emissivity multiplied by the kinetic temperature. So this gives approximately 1/3 the radiant temperature for the half of the portion which is painted by the polished shiny surface. This is going to give the temperature 136.2 degree Kelvin, which is very less in comparison to the kinetic temperature or the true temperature. And for the remaining half, when the radiometer is placed near to the surface to detect the radiant temperature, so since the emissivity is increased and it is near to 1, this is 0.98. So here you can see that very high temperature or near to the kinetic temperature is generated, and the radiant temperature is approximately 286.5 degree Kelvin. That is near to the kinetic temperature. So here you can see that even when the kinetic temperature of the two objects are same or similar, but if there is change in their emissivity, the radiant temperature will be different. So that we can see that by changing the emissivity, even if the objects will having the same kinetic temperature, their radiant temperature detected by the radiometer will be different. Now we are going to talk something related to emissivity. The world is not composed of radiating black bodies, rather it is composed of the selectively radiating bodies such as rocks, soil, and water that emit only a fraction of energy emitted from black body at the same temperature. Emissivity is the ratio between the radiant flux exiting a real world selective radiating body, that is represented by Fr, and a black body at the same temperature, that is represented by Fb. So the ratio of Fr and Fb is going to give the emissivity. So we are calculating the emissivity of any object with the help of this ratio of the radiating flux. Now, all selectively radiating bodies have emissivity ranging from 0 to 1. They will have the emissivity greater than 0 and less than 1, and that fluctuate depend upon the wavelength of the energy being considered. A gray body outputs a constant emissivity that is less than 1 at all wavelengths. Some materials like distilled water have emissivities close to 1, that sometimes we are getting 0.99 over the wavelength interval from 8 to 14 micrometer. Others such as polished aluminum and stainless steel have very low emissivities. Polished aluminum will have the emissivity of 0.08 and stainless steel will have the emissivity of approximately 0.16. All the metallic objects, they are going to have a very low emissivity. They are having very low emissivity. Now, two rocks lying next to one another on the ground could have the same true kinetic temperature but have different apparent temperatures when sensed by a thermal radiometer, simply because their emissivities are different. The example we have seen in the previous slides. The emissivity of an object may be influenced by a number of factors, and those factors includes the color. So darker color objects are usually better absorbers and emitters because they have higher emissivity in comparison to the lighter color objects, which tend to reflect more of the incident energy. It means that when an object is going to reflect the thermal infrared more, it means that they will they will be poor absorber, and finally if they are poor absorber, they will be poor emitter. Now the second factor is surface roughness. The greater the surface roughness of an object related to the size of the incident wavelength, the greater the surface area of the object and potential for absorption and re-emission of energy. Now other factors are the moisture content. The more moisture an object contains, the greater its ability to absorb energy and become a good emitter. Wet soil particles have a high emissivity similar to water. And the next factor is field of view. The emissivity of a single leaf measured with very high resolution thermal radiometer will have different emissivity than an entire tree crown viewed using a coarse spatial resolution radiometer. So emissivity is also going to depend on field of view. When we are coming to the wavelength, the emissivity of an object is generally considered to be wavelength dependent. For example, while the emissivity of an object is often considered to be constant throughout the 8 to 14 micrometer region, its emissivity in the 3 to 5 micrometer region may be different, because we cannot expect that the object will have the same emissivity in the entire range of the thermal spectrum. Emissivity also depends on the viewing angle. The emissivity of an object can vary with the sensor's viewing angle. We must take into account an object's emissivity when we use our remote radiant temperature measurement to measure the object's true kinetic temperature. This is done by applying the Kirchhoff's radiation law. So in the next slide, we are going to talk about the Kirchhoff's radiation law. So first, we are going to understand the interaction of thermal radiation with the terrain elements. When the thermal radiation will hit the Earth's surface, so generally it is expected that there will be three phenomena. One will be some portion of the incident electromagnetic radiation will be reflected, some portion will be absorbed, and some portion will be transmitted through it. So it means that the reflectance plus transmittance plus absorbance, they all will be there and will be equal to 1. How it is going to equal to 1, that we are going to see. Suppose here in this slide, suppose EI is representing the incident thermal energy. EA is representing the portion of the incident energy which is absorbed by the object, and ER is representing the portion of the reflected energy which is incident, and ET is representing the portion of the incident energy which is transmitted through the surface. So here we can see that EI is divided in three parts, that those parts are absorbed energy, reflected energy, and the transmitted energy. Now when we will divide the this with the incoming radiation, so here EI divided by EI, this will become 1. Now EA divided by EI, this is representing the capability of the surface to absorb the incoming radiation. So this is known as absorptance. Now when we are coming to ER divided by EI, that is showing the capability of the or capacity of the surface to reflect the incident radiation. So this will be known as the reflectance. And the third one is the capacity of the surface which can transmit the incoming radiation. So this will be the transmittance. So here you can see that transmittance is represented by tau. This is the transmittance of the terrain element. Rho is representing the reflectance here, and alpha is representing the absorptance of the terrain. So when we are going to take the sum of a reflectance plus transmittance plus absorptance, that will be equal to 1. Now Kirchhoff's law of radiation says that the emissivity at a particular wavelength will be equal to the absorptance of the surface. So here in the same relation, like absorptance plus reflectance plus transmittance equals to 1, here absorptance is replaced by the emissivity. So emissivity plus reflectance plus transmittance is equal to 1. Now if you will see the earth surface, so most of the objects on earth surface, they are opaque in nature. They will not allow any thermal radiation to pass through it, to transmit through it. So at that time transmittance will be equals to 0. Now when transmittance becomes 0, it means that the total incoming radiation will be depending on the two factors, and these are the absorptance that is replaced by your emissivity and the reflectance. It means that reflectance plus emissivity will be equal to 1. Now from this relation we can see that when emissivity will be very high, it means that suppose emissivity is near to 0.8, so we know that sum of emissivity and the reflectance should be equals to 1. At that time the reflectance will become low, the reflectance will become 0.2. Now suppose reflectance is very high, suppose this is 0.8 or 0.9, at that time emissivity will become either 0.1 or 0.2, because the sum will be equals to 1 only. So what is the final conclusion of this relation? The relation says that good reflectors are poor absorbers, and finally poor reflectors. Sorry, not reflectors, poor emitters. Good reflectors are poor emitters, and good absorbers are poor reflectors. So here we can see that since all the metallic objects, they are very good reflector, so that they will be poor absorber and poor emitter, so that for the metallic objects we are going to get the emissivity very low, and for the dark color objects like dark carbon particle, if the surface is having dark color, so at that time what will happen, the emissivity will be very high and the reflectance will become very low. Now we, after seeing the factors which are influencing the emissivity, now we are going to talk about the thermal properties of the terrain. So here we are going to see water, rock, soil, vegetation, the atmosphere and the human tissues all have the ability to conduct heat directly through them. That is known as the thermal conductivity onto another surface and to store heat. So store the capacity to store the heat, that is the thermal capacity. Some materials respond to change in temperature more rapidly or slowly than the others. So this is defined by the property that is known as the thermal inertia. So we are going to have a look on these properties. So thermal capacity is the ability of a material to store heat. It is measured as the number of calories required to raise a gram of material. That is like here when we are talking about water. So here we are talking about the 1 degree centigrade. Water has the highest thermal capacity, that is measured as 1. It stores heat very well related to all the other materials. Now when we are coming to thermal conductivity, that is represented by K. This is the rate that heat will pass through a material and is measured as the number of calories that will pass through a 1 centimeter cube of material in 1 second when two opposite phases are maintained at 1 degree difference in the temperature. The conductivity of a material is variable due to soil moisture and the particle size. Many rocks and soils are extremely poor conductors of heat. Now when we are coming to thermal inertia, that is represented by P. Thermal inertia is measurement of thermal response of material to temperature change and is measured in calories per square centimeter per second square root per degree Celsius. Thermal inertia is computed with the help of the formula that is given here. P equals to K square root of K multiplied by P multiplied by C, where K is thermal conductivity, P or rho is density, and C is the thermal capacity. Now here you can see that density is the most important property in this equation, because thermal inertia generally increases linearly with increasing the material density. Now in the real world, it would be wonderful if you could remotely sense each of the aforementioned variables like thermal capacity and thermal inertia and all the thermal behavior or thermal properties of the terrain. So unfortunately this is not the case, because conductivity, density and the thermal capacity must be measured in situ. Nevertheless, it is possible to remotely sense and compute an apparent thermal inertia measurement per pixel in the following manner. A thermal infrared image is acquired over the identical terrain in the night time and in early afternoon. The two images are geometrically and radiometrically registered to one another, and the change in temperature delta T for a specific pixel is determined by subtracting the nighttime apparent temperature from the daytime apparent temperature. The apparent thermal inertia for per pixel is given as, that is apparent thermal inertia is represented by ATI, that will be equals to 1 minus A divided by delta T, where A is the albedo, that is reflectance measured in the visible band of the spectrum for the pixel of the interest, and delta T could be measured by taking the difference. Here you can see the difference of the maximum and the minimum temperature. So for the particular pixel, the maximum temperature we can get in the daytime imagery, and the minimum temperature we can get the nighttime imagery. So the difference of the temperature will be generated for each and every pixel, and that will be represented by delta T. So the relation 1 minus A divided by delta T, that is going to give the apparent thermal inertia, and we cannot directly measure thermal inertia, because according to the formula we have seen that there is a requirement of the thermal properties of the terrain, different parameters which are governing thermal properties of the terrain. But here with the help of the thermal sensor we can measure the apparent thermal inertia, and we can also measure the land surface temperature. Now there are different applications of thermal imaging. Applications are determining rock types, structure, soil types, soil moisture, and it is also used to find out the forest fire. It is also used to find out the land surface temperature. So there are several applications, very wide applications are there. Now here we are going to analyze the diurnal temperature graph of different features. So here you can see that if you will see the diurnal temperature graph of rocks and soils. So here what we are going to see, when they are just after sunrise, when they are getting the thermal energy from sun. So here we can see that there is rapid change in the radiant temperature, which will be changed by the radiometer or thermometer. and in afternoon near to 14 o'clock the maximum temperature will be there, and after that as the time will be increasing, so and near to evening time here you can see that there is decrease in the radiant temperature, and just after sunset here you can see this is rapidly going down, and here you can see that the temperature is going to minimum. So here very high change in daytime and nighttime temperature we are going to get for the rocks and soils, because their thermal inertia, the resistivity to change the temperature is very less. They cannot resist to change the temperature, so that in the daytime imagery they are going to appear as very bright feature, and in the nighttime imagery they are going to appear as very dark feature. Now if you will see the metallic objects, so metallic objects since they are good reflector and they are poor emitters, so here you can see that there is no very much variation in the radiant temperature of the metallic objects. For the damp terrain again we are able to see some variation, and for vegetation and standing water if you will see we are going to see the similar pattern with some difference, because vegetation is showing the higher radiant temperature in comparison to the standing water. But here you can see that since in the night time imagery this will be very bright, because in the night time imagery you can see that the radiant temperature will be very high in comparison to the metallic objects as well as the rocks and soils. So rocks and soils they are going to appear as dark features in the nighttime imagery, and vegetation and water bodies they are going to appear as very bright objects in the nighttime imagery. Like here this is the nighttime image of the Great Lakes. So here you can see that the water body is appearing very bright, because this is having high thermal inertia. This and this can hold the heat also for a longer time period, so that water is appearing very bright. And here you can see that even the water channels these are also appearing very bright. And here you can see that the terrain and the soil this is appearing very brown, very dark, because they are having very less thermal inertia, so that all the energy which is received by the sun all are emitted rapidly before the sunset or just after the sunset, so that in the night time they are appearing very dark. Now this is the emissivity of the different surfaces in 8 to 14 micrometer wavelength range. So carbon powder will have the emissivity approximately of 0.98 to 0.99. Water will have the emissivity of approximately 0.98, and it is also going till 0.99 also. Ice is having the emissivity of 0.97 to 0.98. Plant leaves, healthy plant leaves, they will have the emissivity of 0.96 to 0.99. Plant leaves, if they are dry, they will have the emissivity 0.88 to 0.94. Asphalt will have the emissivity of 0.96. Sand will have the emissivity of 0.93. Basalt will have the emissivity of 0.92. White paper will have the emissivity of 0.90. Wood will have the emissivity of 0.87. Granite will have 0.83 to 0.87. Polished metal will have the emissivity in between 0.02 to 0.21. Aluminum foil will have the emissivity of 0.036. Now in this table what we are going to see, there is very less difference in the emissivity of water like 0.98 and the sand 0.93. Both are having high emissivity. But but if you will see in the nighttime imagery, sand will appear dark and water of a river is going to appear as very bright. But if you will see that the difference in emissivity is only will be approximately of 0.4 to 0.5. But even with 0.05 emissivity difference, there is lot of difference. There is very high difference in the radiant temperature in the nighttime imagery. That is not coming due to the difference in the emissivity. That is mainly coming due to the difference in the thermal properties of the two features, because sand's thermal inertia will be very low in comparison to the water, so that in the nighttime imagery it is appearing darker in comparison to the water. Now we are going to see some thermal infrared sensors. So a detailed list I have given here. We are not going to see the entire list, but here you can see the list of few sensors like ETM plus, TM, TIRS, ASTAR. So similarly AVHRR, ASTAR. So these are given here, and the real list is long, but here we are going to discuss the few sensors. We are not going in detail of all the other sensors. We are going to discuss only few sensors. Like we are going to discuss here INSAT 3D. This was launched in 2013. The INSAT 3D imager is an improved design of VHRR2, very high resolution radiometer. That was the heritage instrument flown on the Kalpana 1 and INSAT 3A mission. INSAT 3D carries a multispectral imager optical radiometer capable of generating the image of the Earth in 6 wavelength bands. Significance for the meteorological observations, namely visible, shortwave infrared, middle infrared, water vapor, and 2 bands in the thermal infrared region, offering an improved 1 kilometer resolution in the visible band for the monitoring of the mesosphere phenomena and severe local storms. Now we are going to see the imager specification. So if you will see the imager specification, so this is the different spectral bands. So VIS, this is having 1 kilometer resolution, and wavelength range is 0.55 to 0.75 micrometer. SWIR is also there, that is short wave infrared, that is 1.55 to 1.70. This is also having 1 kilometer resolution. And there is one band, that is water vapor band. This is having this 0.5 to 7.10. This is having 8 kilometer resolution. Now the thermal infrared bands. So the 2 bands of thermal infrared are 10 point. Those are working. TIR1 is working in 10.2, 10.3 to 11.3 micrometer, and the second band of thermal infrared is, works in 11.5 to 12.5 micrometer, and it is having the resolution of 4 kilometer, special resolution of the 4 kilometer. Now we are going to see the ASTAR thermal infrared band. So due to its high spatial resolution, this ASTAR sensor has been widely used by the scientific community to do the study of the thermal properties for the different applications. So here you can see that there are total here listed 5 thermal infrared band which are used between 8 micrometer to 12 micrometer, and these are having the approximately spatial resolution of 90 meter. And one advantage is that high resolution optical multispectral data set could also be obtained from this sensor, so that this sensor could be used for the different measurements like thermal inertia also, and for different other applications. Now this is also very famous sensor, Nova VHRR3 thermal infrared sensor. So here we are going to see this is also having the VIS band, that is the visible range band. This works in 0.58 to 0.68, then NIR, then SWIR, MIR, and then when we are coming to the thermal infrared range. So thermal infrared range is like the bands are band number 4 and 5. So band number 4 works between 10.3 to 11.3 micrometer. Band number 5 works from 11.5 to 12.5 micrometer, and both are having the spatial resolution of 1.1 kilometer. Now the coarser spatial resolution could not be utilized for the small area. They could be used for the regional studies, or the national, or the international scale studies. These could be used. Means either regional or national or the global scale studies. This could be used because the resolution is approximately 1.1 kilometer. Now Landsat series of the sensor, they have also been used by the scientific community widely for the thermal to or do the study of the thermal properties of the terrain, because they are offering very high spatial resolution of the thermal sensor, as well as they are offering the high uh, uh, high spatial resolution in the multispectral band also. So Landsat 4 and 5. So here you can see that there are 7 bands. Out of 7 bands, band number 6 is the thermal band, and all the other are the bands from the visible range as well as the reflected infrared. And the band number 6 is having the spatial resolution of 120 meter, but the data set is resampled at 30-meter resolution, so that there will be complete overlap of the data set with overlap up to the up to the pixel level matching with the multispectral data set. Now this is the specification of the Landsat 7 sensor. So here again there are 8 bands, and band number 6 is the thermal band, and which is operated between 10.4 to 12.5 micrometer, and the resolution is 60 meter, and but again this is resampled at 30 meter. Now Landsat 8 was launched after this after the launch of Landsat ETM, and currently we can see that a few years back Landsat 9 was also launched. So here in the Landsat series of the satellites, before Landsat 8 we were getting only one band of the thermal data set. After launch of Landsat 8, we have the 2 bands of the thermal 2 bands in thermal infrared, but unfortunately there is error in one band. But anyhow, band number 10 is widely used by scientific community. Here you can see that there are several bands, like band number 1 that is used for the coastal aerosol study, that is in between 0.43 to 0.45. Band number 2 is the blue band, that is 0.45 to 0.51. Green is 0.53 to 59. Red is 0.64 to 0.67. Near infrared, then shortwave infrared. So there are several bands. Total number of bands are 11. Now if we will have any thermal data set, so from the thermal data set we need to convert the data set value. Those values will be the digital number values. The pixels, each pixels will have or each pixel will be associated with a digital number value. So those digital number values should be converted to the spectral radiance, because suppose one is interested to find out the temperature information from the thermal data set. So first step will be to find out the spectral radiance. So spectral radiance is defined as the energy within a wavelength band radiated by a unit area per unit solid angle of measurement. In order to convert the DN from the Landsat series of the data set in spectral radiance, the formula is given below. Li equals to L minimum plus L maximum minus L minimum multiplied by QDN divided by Qmax, where Li is the at sensor spectral radiance, or we can say that the spectral radiance which is sensed by the sensor, and L maximum is the maximum at sensor spectral reflectance value, and N minimum is the minimum at sensor spectral reflectance value. Qmax will be represented, Qmax will be the maximum DN value. So this is going to depend on the radiometric property of the data set, and QDN is representing the DN value associated with the particular pixel for which we are working. Now L minimum and L maximum that could be obtained from either from the metadata, or the space agencies, they are updating the minimum and maximum values, and Qmax could also be obtained from the metadata. So this is the L max and L minimum values for the Landsat 5, Landsat 7 and Landsat 8. So here you can see that for different sensors these values are different, and differently the Qmax that I have told about the radiometric property, that is also very high, particularly in the case of Landsat 8. Now when the data set is converted to the spectral radiance, so again the spectral radiance should be converted to the at sensor brightness temperature. At sensor brightness temperature is basically the radiant temperature. So the radiant temperature will be equals to K2 divided by natural log of 1 plus K1 divided by Li, where Li is representing the spectral radiance which we measured in the previous step. In the previous slide we had seen the formula to calculate the Li. So with the help of these values, the K1 and K2 are the calibration constants. So with the help of these constants, one will be able to find out the at sensor brightness temperature value. So these are the values of the K1 and K2. So here we can see that for different sensors, we are going to get the different calibration constants. Sometimes the calibration constants are also updated for the different sensors by the different space agencies. So one can get the information of the calibration constants, and after that one will be able to find out the radiant temperature. Now when we will have the radiant temperature information, so with the help of the radiant temperature, that is represented by the brightness temperature TB. So with the help of the TB, one can easily find out the land surface temperature or the temperature of the targeted object. So that will be equals to TB divided by 1 plus lambda. Lambda, when we are talking about a particular wavelength range, so lambda is the wavelength of the particular band. Lambda multiplied by TB divided by rho multiplied by the natural log of emissivity. So here the main factor or main challenge is to get the emissivity of the surface. So there are several algorithms and techniques are there to calculate the emissivity. So one technique is NDVI based also, but there are several other techniques also. So based on those techniques, one can measure the emissivity, and after measuring that, land surface temperature could be estimated. Now here as we have talked about, LST is representing the land surface temperature, TB is representing the at sensor brightness temperature, or you can say the radiant temperature, lambda is the wavelength of the particular band, and here when we are talking about rho, so rho is basically H multiplied by C divided by sigma, where sigma is Boltzmann constant, H is Planck's constant, and C is the velocity of the light. So the rho is also a constant value, and emissivity of the surface you will have to measure with the help of the given approaches. Now this is the land surface temperature image which we generated for the city for the year 2009, and this image, land surface temperature image, was basically generated with the help of the NDVI based emissivity retrieval. So using that, the land surface temperature image was generated. That's all from my side.